Welcome to the atom. Today, we embark on a journey into the very fabric of our universe. The atom, though minuscule, holds the secrets to the vast complexities of the world around us. Atoms are the building blocks of everything we see and touch. They are incredibly small, so small that millions of them could fit on the head of a pin. Despite their size, they are the foundation of all matter. Yet they contain a universe of energy within them. This energy is what powers the stars, fuels our technology, and drives the processes of life itself. At the center of an atom is a nucleus. This nucleus is incredibly dense and contains most of the atom's mass. It holds protons and neutrons. Protons have a positive charge while neutrons are neutral. Together they form the core of the atom. Orbiting the nucleus are even tinier particles called electrons. These electrons are negatively charged and are in constant motion around the nucleus. Electrons are constantly in motion. They move so fast that they create a sort of cloud around the nucleus, making it difficult to pinpoint their exact location at any given time. They zip around the nucleus at incredibly high speeds. These electrons possess energy, which is a crucial aspect of their behavior and interactions. This energy is not just some abstract concept. It is a measurable and fundamental property of electrons that affects how they interact with other particles. It is a fundamental property of electrons. This energy determines the electron's position and movement within the atom, influencing the atom's overall behavior. It influences how atoms interact with each other. The energy levels of electrons play a key role in chemical reactions and bonding. Understanding electron energy is key to understanding how our world works. It helps us comprehend the principles behind everything from the simplest chemical reactions to the most complex biological processes. It explains everything from why water boils to how our sun shines. The energy of electrons is a driving force behind many natural phenomena. So, let's dive in and explore the fascinating world of electrons and their energy. By understanding these tiny particles, we unlock the mysteries of the universe and gain insights into the very essence of matter. The electrons dance energy levels in the atom. In the microscopic world of atoms, electrons are not just aimlessly wandering around the nucleus. Instead, they follow specific paths and occupy distinct regions known as energy levels. These energy levels are crucial to understanding the behavior of atoms and the formation of chemical bonds. Electrons don't just randomly orbit the nucleus. They are organized into specific energy levels, much like how planets orbit the sun in our solar system. Each electron's position is determined by its energy, and these positions are not arbitrary. They are organized into specific energy levels. These levels can be thought of as layers or shells surrounding the nucleus, each with a certain capacity to hold electrons. The arrangement of electrons in these levels determines the chemical properties of an element. Think of these levels as a set of stairs. Just as you can only stand on one step at a time, an electron can only occupy one energy level at a time. The higher the step, the higher the energy level. Each stair represents a different energy level. The first step, closest to the ground, represents the lowest energy level, while higher steps represent higher energy levels. Electrons closest to the nucleus occupy the lowest energy level. This is because they have the least amount of energy and are most strongly attracted to the positively charged nucleus. This is like being at the bottom of the staircase. The closer you are to the ground, the less energy you need to stay there. Electrons farther away occupy higher energy levels. These electrons have more energy and are less tightly bound to the nucleus, allowing them to move more freely. They are higher up on the staircase. Just as climbing higher steps requires more effort, electrons in higher energy levels have more energy. Just like climbing stairs requires energy, so does moving an electron to a higher energy level. This energy can come from various sources, such as absorbing light or heat. This energy can come from various sources like light or heat. When an electron absorbs energy, it can jump to a higher energy level, much like how you can climb to a higher step if you have enough energy. Conversely, when an electron drops to a lower energy level, it releases energy. This release of energy can be in the form of light or heat, and it is a fundamental process in many chemical reactions. This energy release is the key to understanding why electrons release energy when bonding. The movement of electrons between energy levels is not just a fascinating phenomenon, it is the driving force behind the chemistry that shapes our world. Seeking stability, why lower energy is better. In the universe, everything strives for stability. From the vast galaxies to the smallest particles, the quest for balance is a fundamental principle. This drive for stability is evident in the way celestial bodies move and interact, maintaining a delicate equilibrium. It's like a ball rolling downhill. Imagine a ball placed on a slope, it will naturally roll down to the lowest point. This is because the ball is seeking a state of lower energy, where it can rest without any external force acting upon it. The ball will naturally seek the lowest point, where it is most stable. Atoms are no different. Just like the ball, atoms and their electrons are constantly seeking the lowest energy state to achieve stability. They want their electrons to be in the lowest possible energy levels. Electrons in an atom prefer to occupy the lowest energy levels available to them, minimizing the energy of the atom and making it more stable. This state of low energy represents stability for the atom. When electrons are in these lower energy states, the atom is at its most stable, much like a calm lake that remains undisturbed. When atoms have electrons in higher energy levels, they are in an excited state. This is a temporary and unstable condition, as the electrons are not in their preferred lowest energy positions. This is like the ball being stuck halfway up the hill. It has the potential to roll down to a more stable position, just as electrons in higher energy levels have the potential to move to lower levels. It has the potential to roll down and release energy. When electrons transition from higher to lower energy levels, they release energy, often in the form of light or heat, similar to how the ball releases potential energy as it rolls downhill. This drive for stability, for electrons to occupy the lowest available energy levels, is what drives the process of chemical bonding. Atoms bond together to achieve a more stable, lower energy state, forming molecules and compounds that make up the world around us. The bonding process, a dance of attraction. Atoms rarely exist in isolation, they are constantly interacting with each other. One of the most important ways they interact is through chemical bonding. Bonding occurs when atoms share or transfer electrons to achieve a more stable, lower energy state. Imagine two atoms, each with electrons in different energy levels. As they approach each other, their electrons interact. This interaction can lead to a rearrangement of electrons. Electrons from one atom might shift to lower energy levels in the other atom. This shift to lower energy levels releases energy. It is this release of energy that we observe as heat or light during chemical reactions. Section 5. Releasing the heat energy's grand exit. The energy released during bonding doesn't just disappear, it has to go somewhere. This energy is released into the surroundings. We experience this energy release in different ways. Sometimes we feel it as heat. For example, when we burn wood, the chemical bonds in the wood are broken and new bonds are formed, releasing energy as heat and light. Other times the energy release is less dramatic but equally important. For instance, the batteries that power our devices rely on chemical reactions that release energy in the form of electricity. Understanding energy release during bonding is crucial for developing new technologies, from more efficient batteries to cleaner fuels. Section 6. From atoms to us, the impact of bonding energy. The energy released during bonding isn't just a scientific curiosity, it has profound implications for life itself. The reactions that sustain life, from photosynthesis to digestion, all involve the making and breaking of chemical bonds. These reactions release the energy that powers our cells and allows us to move, think, and exist. Without the precise release of energy during bonding, life as we know it would not be possible. Every breath we take, every bite of food we eat, is a testament to the power of electron energy and the importance of chemical bonding. Section 7. The future of bonding, new discoveries await. While we understand the basics of electron behavior and bonding, there is still much to explore. Scientists are constantly developing new techniques to study these phenomena at incredibly small scales. These advancements are leading to new discoveries about how electrons behave in different materials and under extreme conditions. These discoveries have the potential to revolutionize fields like medicine, energy production, and computing. The future of bonding is bright, and the discoveries yet to be made promise to reshape our understanding of the universe and our place within it. Section 8. Energy and life, the fundamental connection. The release of energy during bonding isn't just a chemical phenomenon, it is a fundamental principle woven into the fabric of the universe. From the nuclear fusion that powers stars to the chemical reactions that drive life, energy release is essential. Understanding this connection helps us appreciate the intricate balance and elegance of the natural world. It reminds us that even the smallest particles, like electrons, play a vital role in shaping the universe we inhabit. By studying these processes, we gain a deeper understanding of our own existence and our place in the grand scheme of things. Section 9. Conclusion: the universe in a chemical bond. In the end, the story of why electrons release energy when bonding is a story about the universe's quest for stability, the interconnectedness of energy and matter, and the elegant simplicity of nature's laws. From the tiniest atom to the largest star, the same principles apply. Energy drives the dance of particles, shaping the world around us in ways we are only beginning to understand. As we continue to explore the mysteries of the atom and beyond, we can be sure that the release of energy during bonding will continue to play a central role in our understanding of the universe and our place within it.